Hi everyone, welcome to Unit 3 Polynomials. Today we're on Lesson 1. We're going to be talking about characteristics of a polynomial. So first off, what is a polynomial function? It's basically any function with a coefficient, variable, and some sort of exponent usually there as well. And we are always writing these functions from greatest to least in descending order for our exponents. So whatever our largest exponent is, and then the next largest, all the way down until you get to x squared, x, and then no variables there at the very end. So let's go through a few of our variables here. So we have n, which is always a whole number. So whole number meaning anything greater than 0. No decimals, no fractions. X is always going to be our variable. And then you have coefficients, n to a naught or a 0 there. Basically, these are only numbers. They could be any real number. There could be decimals, fractions. Usually we'll keep two whole numbers or integers at most. So, in example 1 here, we're asking you explain why the following are not polynomial functions. So what makes these examples not a polynomial function? So right away in this very first example, hopefully you see, is there's 1 divided by x. So this 1 over x here, this is going to make it not a polynomial function. 1 over x is the same thing as saying x exponent negative 1. If you go back to our quick rules right up top here, our n value, our exponent has to be a whole number. Well, negative 1 is not a whole number. Again, whole numbers start at 0 and going up. So basically here, x equals negative 1. I found it in this function here, so therefore we're not a polynomial because you can't have negative exponents. In this next example here, if you take a look at this function, 8x, that 2 is all good, but again, right at the beginning there, we have a radical. This square root 4x, if you wanted to try to clean it up, let's see what we can do. Square root of 4x is going to be 2, because square root of 4 is just 2, and x here is now going to be x to the 1/2. So I just changed from radical back to an exponent. Well, again, 1/2 is not a whole number. Whole numbers have no decimals, no fractions. So therefore, this can't be a polynomial function because you can't have fractions. So really it's fractional exponents. In this third example here, let's take a look. X squared is good, plus x squared is good, minus x, that's usually good there, but we have this negative 1. And again, same reason as the beginning here, you can't have a negative exponent, so x negative 1 there. It doesn't matter where that was found in the equation, therefore can't have negative exponents again. So it says here if f of x equals 4, is f of x equals 4 a polynomial function? Explain why or why not. In this example here, so basically it's just telling you if you have a constant term, if it's just a constant number, no exponents or no variables there, is it a polynomial? Technically, I believe we can make it into a polynomial. Let's see what we can do. So we can change f of x equals 4. That's our standard equation there that they gave us. Let's add on x exponent 0. Well, x is just a variable. Exponent 0, I'm allowed to have exponent 0 there because n can be a whole number. Whole numbers start off at 0. So if I rewrote this as 4x exponent 0, then therefore, yes, it is a polynomial. So therefore, yes, it is a polynomial. Great. On the next page here, we have some key terms that we're going to be always referring to. The first one is degree. It's the greatest exponent of the variable. So in this example here, you're looking at the exponents. We have 4, 2, and technically this has exponent 0. Of course, let's add that in case you forget. X exponent 0 is always just 1 there. Our greatest exponent, our biggest degree, is going to be degree 4. Leading coefficient is always the is always the numerical coefficient of the highest degree variable. So again, you have coefficients of -5, 3, and 6. The leading coefficient, the one on the highest degree, is going to be -5. In the next one, constant term, you're always looking for the term without a variable, i.e. x exponent 0. X exponent 0, of course, is just 1. Our constant term here, +6 or just 6. End behavior. End behavior is new. This is the newest one that we're going to be talking about here. It's the behavior of the y values of our function. Basically, becomes a very small or a very large. So in this example, it's best to describe it in an example. So if I had a graph, okay, and that's my grid there. If I had a graph, and let's say we had it looking something super funky like this, almost like a letter M almost, both pointing down. So here to describe end behavior, you're always asking yourself, reading it left to right, where did it start and where does it end? This arrowhead started off in quadrant 3 and it's moving to quadrant 4, and so that would be end behavior. So it's going from 3 to 4. It's also, just a side note, it's in the negative quadrant and it's still continuing to be negative right there. So again, that's end behavior. On this slide here, we have a large chart or a large table here that we want to fill out. We want to fill in as many of these functions as possible. So number one, we're going to sketch everything, fill in the degree, leading coefficient, and behavior. Again, that's just working with quadrants. So quadrants 1, 2, 3, 4. So we're talking about which way did it start, which way does it end, going left to right always, always. Number of zeros. So again, that's your number of x-intercepts and your actual y-intercept here. What I would strongly suggest for you to do is to graph all of these functions out and see what they kind of look like. I would graph using a graphing calculator, that is. So the very first one here, just an FYI, as I know this one here, x minus 3, that's just a straight line. X minus 3 means it's a straight line going through a y-intercept of -3 there. There's going to be a double arrowhead, so I already have one on the very far right there. I'm going to add an arrowhead here on the far left, just showing that that graph is going to go on forever. To fill in some of these here, we have degree 1, because this is x exponent 1, so degree 1. Leading coefficient is also 1. What's our end behavior? We started off in quadrant 3, we ended off in quadrant 1, so we can say something like quadrant 3 to quadrant 1, and we could talk about the y values as well. So this is going from a negative y value to a positive y value. Number of zeros, aka how many x-intercepts do we have? We only have one. It's only crossing our x-axis once. And what's our y-intercept? Our y-intercept is at 0, -3. So that's our first graph here. Our second graph here, and again, I'd strongly suggest for you to graph all of these on your graphing calculator, and if you have troubles with it, please let me know. So this second one here is going to look something like an upside down parabola. Sorry, my parabola just did not work out there. Let's try to redraw that. There we go. That's as good as it's going to get, unfortunately. So there's my parabola, drawing arrowheads on the end of it. I definitely cross here, and I had a y-intercept here. So let's figure out some of these characteristics. Again, what's our degree here? Our largest exponent is a degree 2. We have a leading coefficient of -1 on that. We're going from quadrant 3 down to quadrant 4. And this is going from a negative y value and continues being a negative y value overall. Here, how many x-intercepts do we have? We have 2 x-intercepts, and again, they'll be found right here and right here. 2 x-intercepts, and on this last one we only had 1. So we have 2 x-intercepts. And what's our y-intercept? Well, our y-intercept was just this little guy up here. That's going to be at 0, 2, +2. This third graph here, It looks like we're working on a cubic function now. So this is 2x cubed minus 3x squared. So make sure that you know where that cubic function or your exponent button for cubes are on your graphing calculator. Again, I would graph these out. So just going to put a dot there real quickly. That's going to help me draw in my graph. And your graph should have looked something similar to this on your graphing calculator. I'm going to try my best to stick to the same coloring for a few of this. So, what's our degree again? Our degree, we're on degree 3 because it's cubic. Leading coefficients, the number 2. We started off in quadrant 3 and we're ending up in quadrant 1. So you went from negative to positive for y values. How many x-intercepts do we have? We have 3 x-intercepts, or 3 zeros. And what is our y-intercept? We only have one of them, and it's going to be at 0, comma, positive 1. On this next one here, again, it's something cubic, but again, double check your equation. We're typing all this into your graphing calculator. You should end up with a graph that looks something like this. So it's a U, it's a U shape that's gonna go up a bit, and then it's gonna go down. That's what you should have had on your graphing calculator. So it's like a slight U, and then it goes up, and then it goes back down. So again, we have a degree 3. This time we have a leading coefficient of -1 on that number. We're in quadrant 2 this time, and we're going off to quadrant 4 there. So that means we're starting on a positive value, and you went negative in terms of y values. In this graph here, we only have the one x-intercept. Don't care where it is, it's just asking you where, how many you had in this column here, and our y value, our y-intercept is going to be at 0, comma 15. These next few, here we go. So this is x exponent 4 there. For x exponent 4, we're going to have a graph that looks something like this. There we go. And that's our x exponent 4 graph. So right now we have degree 4. Oh, and I forgot to color in a few of these x-intercepts. So we have degree 4, the leading coefficient is a positive 1. We're in quadrant 2 going off to quadrant 1. So quadrant 2 going off to quadrant 1, we were positive and we ended up positive. So we started positive, ended up positive, going left to right. So positive here, still positive up here. We have, it looks like 4 x-intercepts, and our y value in this case here is going to be at 0, 0. That's our y-intercept. On this next one here, again degree 4, minus 5, so what's that going to look like? It looks kind of like this here, like a giant U, but more squared off. There we go. So that's this graph here. And again, this is degree 4, ooh, wrong color. So we are degree 4, leading coefficient of 1. We're in quadrant 2, going off to quadrant 1. Still positive to positive in terms of y values. In this case here, we only have our 2 x-intercepts, but that's fine. And we have a y-intercept at 0, comma, -5. There we go. This second to last one here is exponent 5, so it's going to look kind of funky, so hear me out. It's going to start up here, it's going to go dip down, right back up. Oop, my graph is not working out. It's going to go up, dip down here, go back up, and go back down. So it kind of looks like a very, very squiggly line in this case here, and I'm just going to try to clean that up as best as I can. Oop, took out too much there. So that's what our graph should have kind of looked like, a bit more rounded off, of course. So what do we have in terms of characteristics? We have a degree 5, because that's my largest exponent. Leading coefficient is -2 on there. We're starting off in quadrant 2. We ended up in quadrant 4. So that means we started off positive y values and we're ending up as a negative y value most likely. In terms of 1, 2, 3, 4, 5. In terms of x-intercepts, we definitely have 5. I'm just counting out 5 there. And in terms of our y-intercept, we seem to be crossing out 0, 0. Last but not least, here we go. It's going to be this graph here. So I'm going to start off our graph. It looks something like this. It's going to dip down. It's going to go back up a bit. It has a slight dip and then even further up. There we go. So on this one here, again, we're degree 5, leading coefficient's +1. We started off in quadrant 3, ending off in quadrant 1 there. So we're starting negative, going positive in this case here. Our number of x-intercepts in this case I see is 1, 2, 3 x-intercepts. And it looks like I have a y-intercept at 0, -1. There we go. So it's always good to refer back to this chart, by the way, once you have it all nice and filled out now. Refer back to this chart. So we're basically comparing your degrees. So you have degree 1, degree 2, degree 3s here. I gave you 2 examples. Degree 4, I gave you 2 examples, but one of them's not, none of them were negative, but you can kind of picture what it's going to look like negative. They'd be both be going down. And then you have degree 5 down here. It's a squiggly line. So let's take a look even closer at these characteristics. So taking a look at the degree of the polynomial is going to tell you or indicate the maximum number of x-intercepts or zeros, right? So here, if my largest degree is 5, it's going to have a maximum of 5 x-intercepts. Degree 1 here, so I'll have a max of 1 x-intercept. And of course here, if it's just a number, we're not going to have any x-intercepts. Well, you'll have 0 x-intercepts there. So some quick notes. If your degree is odd, your ends will point in opposite directions. So if you take a look at degree 1, which is a straight line, degree 3, which kind of looks like this in terms of a squiggle line, and degree 5 was a squiggle line that also ends in different directions. So they'll always end in opposite directions. Evens will always end in the same direction. So degree 2, so aka our parabola, ends in a U shape going up, and even like a degree 4 would look something like you could have a squiggle there, but yet it end up in the same direction. It almost looks like the letter W. Leading coefficients will tell you if you're reflecting over the x-axis or not, so basically a negative or positive graph. And your constant term always tells you your y-intercept. If you didn't notice that in the previous table here, all our constant terms, -3, that's our y-intercept, 2, y-intercept, 1, y-intercept. So all of our constant terms are always our y-intercepts. If there's no constant term, y-intercept has to be 0 by default. Here in example 2, we're just going to graph these examples out as best as we can using the descriptors that they gave us. So let's see what they have. So we have a polynomial with degree 3, so that means right away if it's degree 3, I'm ending in opposite direction. So just opposite direction. So opposite OPP direction. A positive leading coefficient, that means you'll go left to right, is from quadrant 3 up to quadrant 1, because that's a positive leading coefficient, so you're always in this kind of direction. Oops. In a left to right going upwards trend. And 2 x-intercepts. Okay, so 2 x-intercepts. So if I'm a degree 3, 2 x-intercepts, I'm just going to draw on my grid here 2 x-intercepts. It doesn't tell us what it is. We're just basically sketching as best as we can here. I'm going to put one there, and let's say one at, I don't know, 1, 2, 3, 4, just to make it interesting, just to give us good x-intercepts right there. I can do anything in terms of my graph as long as I start off in quadrant 3 somehow and end up in quadrant 1. So I could even do something like, hey, let's draw a tail end down here. Let's do our loop right through here, and if you wanted, hey, we cross through a y-intercept of 3 there. From here, I can turn right up, and it looks something like that. So this is just an example, and that's what I would do is I would sketch in a few of these characteristics. So make sure you know how it's going to look overall. Degree 4, so again, degree 4 is going to have either um, same direction, you're ending up in the same direction somehow. So I'm going to write a quick note, same direction. If it says we have a leading or a negative leading coefficient, that means we're going to end up down. And 4 x-intercepts. Okay, so let's draw on 4 x-intercepts somewhere. Let's pick again, just pick something easy. I'm just gonna pick -1 there. Sure, why not? Let's pick a different number. Let's do 3. Let's do, I don't know, something at the end there, and let's choose, I don't know, 4, 3, or 4 right there. So if I have 4 x-intercepts, as long as I have 4 dots somewhere on my x-axis, I'm good. If it's a negative leading coefficient, that means both arrowheads have to be in the negative direction. It's down here somewhere. So here we go. So right away from my last coordinate, I'm going to draw a line straight down. That's where it's going to go. So from here going, I got to connect to that next one. So let's draw a little hump over. Sure, why not? Let's do one of these guys there, a little bit smaller. Let's do something a bit larger. There you go. And then it goes right through that last dot going down. There we go. That's going to be my example for something like this. In example 3, it's asking you to determine the function if it's even or odd based off the graph, what the leading coefficient might be, positive or negative, state the number of x-intercepts, state the domain and range this time, so something kind of new. So in this case here, what do we have? Do we have an even or an odd degree? So if we have arrowheads going in the same direction, we have an even degree. So even degree. And again, it's because it's the same direction, because same direction. The next question was the leading coefficient positive or negative. Well, in this case, they're pointing up, so it has to be a positive coefficient. Positive leading coefficient. Because they're both going up. Up next, the question was asking how many x-intercepts do we have? So let's take a look at our graph. Well, we only have, sorry, there's 1, there's 2. Sorry, that first circle didn't really work out. But you have 2 x-intercepts. So that's what we're going to write down. So we have 2 x-intercepts. And the last question here, what's our domain and range? So domain, how far left and right are we going? Well, let's do this in terms of set notation for this first one. X such that we're going as far left as negative infinity, as far right as positive infinity, so where x is an element of a real. We're going to be a bit of everything. For our range, what's our lowest, what's our highest? So we got y such that our lowest, it looks like, and it gave us coordinates, lowest is -5. Our highest is going off to infinity. So y has to be greater than or equal to -5, and y is going to be an element of a real. There you go. So that's this first graph. For our next graph, example B, let's take a look at even or odd degree. Well, we have arrowheads going in different directions, they're opposite directions. So we have an odd degree this time, so odd degree. And again, that's only because our arrowheads were going in opposite directions. Is it a positive or leading coefficient? Well, going left to right, are we ending off on a positive or a negative answer? So left is negative, right here is positive. If you trace it left to right, we end off on a positive. So it's a positive leading coefficient. Up next is x-intercepts. So it looks like we have 1, 2, 3, 4, and yep, we could definitely have 4 in a graph like this. maybe even about 4 or 5. It looks like this one here dips down again, so I think there's actually 5 there. So we got 5 x-intercepts. And last but not least, let's do domain and range. Domain, range. In this last question we did set, so this time let's do interval notation. So how far left and right are we going? Going as far as negative infinity to positive infinity. And lowest to highest is also from negative infinity to positive infinity. There we go. Rounded brackets on both, and that finishes off this question. On our last example here, example 4, so again we're just taking a look at these equations and trying to state some of these characteristics. So for each function, use the degree and the sign of the leading coefficient to describe the end behavior of its graph, state possible x-intercepts, and the value of the y-intercepts. Okay, so in this case here, let's take a look at just this very first term. That's really what I'm looking for, and this is the largest term out of the equation. It was sorted properly. So this here has a degree. Our degree is going to be 5. Our leading coefficient on there, so leading coefficient's the number 4. And so what does that mean? So degree 5, it says using the degree and the sign of the leading coefficient describe end behavior. So for degree 5, our end behavior, let's talk about end behavior, because its leading coefficient's a positive leading coefficient, so most likely we went from a negative to a positive in terms of y values. And if it's degree 5, it's negative, it's usually in quadrant 3, positive in quadrant 1. So quadrant 3 going off to quadrant 1. Our x-intercepts, so let's talk about that. X-intercepts is going to be based off of degree. If it's degree 5, we could have a maximum 5 possible, so maximum maximum 5 possible x-intercepts. You could have less than 5 for sure, but 5 would be the most x-intercepts that you could have in this example here. And the value of the y-intercept, of course, it's always going to be this constant term right at the end there, so our y-intercept is at 0, 2. On this next one here, again we're going to take a look at the leading coefficient. In this example, if you notice, degree 4, degree 5, this wasn't sorted properly, so even if it's not sorted properly, you still need to take the highest degree. So in this case here, our degree is going to be degree 5 again, leading coefficient. This time is a negative 2. So again, how many possible x-intercepts? We'd have 5 possible x-intercepts. Leading coefficient negative 2, meaning you're going from a positive to a negative value. So you went from positive y value to negative, and the only way to go from positive to negative is if you went from quadrant 2 down to quadrant 4, in this case here, diagonally down. You also have a y-intercept here. It doesn't, where is it? It doesn't mention what it is. Like it should be plus 0 there, so you'll have a y-intercept at 0, 0. Oops, there's my coordinates. There we go. So that's this second example here. Our third example, again, let's take a look through our equation. We're looking for the highest degree. Highest degree here is, let's box that off there, degree 3. So in this case we have degree 3, leading coefficients a negative 7. So with degree 3, maximum of 3 possible x-intercepts, so max 3 x-intercepts. And again, you don't always have to have 3 x-intercepts. You could have 2, 1, it doesn't matter. Leading coefficients negative 7, so that means you're going from positive down to negative somehow. So in this case here, we would be, let's say, positive to negative y value. you're only positive in quadrant 2, ending up in quadrant 4 to be negative. We have a y-intercept, and again, y-intercept is going to be right there at the end. It's our constant term, so we have a y-intercept at 0 comma negative 6 is what I'd expect to see. On this very last one here, again, hunt down the largest exponent right here. So we have degree 5. Leading coefficient is 3. So you have potential of max 5 x-intercepts. You have a leading coefficient of 3, meaning that's a positive number. That means you're going from negative to positive. In terms of your y values, it's a negative to positive. You ended up positive. So if it's degree 5, it's most likely quadrant 3 up to quadrant 1 for negative to positive. And of course, we do have y-intercept right there at the end. That's going to be at 0 comma positive 3. Alright, and that was the last example for today. If you have any questions, please see me in class.